Welcome to Ultimate Sleep Doctor. Tonight, we turn our gaze outward into the quiet majesty of our solar system. Around our sun, a dance of immense power and elegant distance unfolds. Each planet, a world of its own, spinning in a timeless ballet. Consider the scale of it all, vast oceans of space, the silent journeys of light years. There's a comforting order to this cosmic arrangement, a balance that's existed for billions of years. If you find these explorations soothing, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Just breathe, let your thoughts drift, and allow the beauty of space to settle within you. Let's begin. Once upon a time, far, far away, in a region of space now known as the Orion arm of the Milky Way galaxy, there was a cloud. Not a fluffy, white cloud like those that drift across our sky, but a vast, swirling cloud of gas and dust. This wasn't just any cloud, it was a stellar nursery, brimming with the raw materials needed to create a star, and potentially a whole solar system. This cloud, primarily composed of hydrogen and helium, remnants of the Big Bang itself, was disturbed. A shockwave, perhaps from a nearby supernova, the explosive death of a massive star, sent ripples through the cloud, initiating a slow, graceful collapse. The initial collapse wasn't sudden and violent. Instead, gravity, the ever-present force that pulls everything together, began to exert its influence. The cloud started to spin faster and faster as it contracted, like a figure skater pulling in their arms to speed up a spin. This spinning motion is crucial to the story of our solar system's birth. As the cloud spun, it flattened into a swirling disk, a protoplanetary disk, with the majority of the mass concentrated in the center. This central point, where the spinning was most intense, would eventually become our sun. Within this protoplanetary disk, tiny dust grains, each just a fraction of a millimeter in size, began to collide. These collisions weren't random. The conservation of angular momentum, that the spinning motion doesn't just disappear, meant that these grains stuck together. They gradually grew larger and larger, attracting more and more dust through a process called electrostatic attraction. It's like a tiny magnet attracting small pieces of metal. Over millions of years, these small clumps of dust merged, forming pebble-sized objects, then larger rocks, and eventually kilometer-sized bodies. This stage is known as accretion. The conditions within the disk were surprisingly chaotic. There were gaps and clumps of denser material, and areas where the gas was hotter and denser than others. These variations in density played a critical role in the formation of the planets. Close to the sun, where it was much hotter, only rocky materials could survive. The intense heat vaporized any ice or volatile compounds, leaving behind materials like iron, silicon, and magnesium, the building blocks of the terrestrial planets, Mercury, Venus, Earth, and Mars. Further out, beyond the frost line, a boundary defined by the temperature, it was cool enough for ices like water, methane, and ammonia to exist. These ices significantly increased the amount of solid material available, allowing for the formation of much larger objects. These larger objects, composed of rock and ice, were the seeds for the gas giants, Jupiter and Saturn. Jupiter and Saturn, being so far from the sun, had enough time for their cores to grow to enormous sizes, attracting vast amounts of hydrogen and helium gas from the surrounding disk. This process is what transformed them into the massive, gas-rich planets we know today. Meanwhile, the remaining material in the disk, particularly the icy components, continue to accrete, forming a belt of smaller, icy bodies, the building blocks of the outer solar system. These objects, now known as planetesimals, continue to collide and merge, gradually growing into the moons that orbit the gas giants. The entire process of accretion wasn't smooth or predictable. Giant impacts were commonplace. A Mars-sized object, often referred to as Theia, is believed to have collided with the early Earth. This impact blasted a vast amount of material into space, which eventually coalesced to form our moon. The moon's formation is a direct consequence of these violent collisions, a fascinating example of how chaotic and dynamic the early solar system was. It's important to remember that the protoplanetary disk didn't just magically spit out planets. It was a complex, ongoing process of gravitational attraction, collisions, and accretion, lasting tens of millions of years. The timing and distribution of this process, influenced by the initial conditions of the cloud and the subtle variations in the disk's density, ultimately determined the configuration of our solar system. The sun, born at the heart of this swirling disk, began to shine brightly, emitting powerful solar winds, streams of charged particles. These winds pushed away much of the remaining gas and dust, clearing the protoplanetary disk and leaving behind a relatively quiet solar system. The planets, now gravitationally bound to the sun, began their orbits, tracing out stable paths dictated by Newton's laws of motion. Each planet's orbit is slightly eccentric, not a perfect circle, reflecting the somewhat uneven accretion process that shaped its formation. Looking back, the formation of our solar system is a remarkable tale of cosmic choreography, a testament to the power of gravity and the incredible potential for complexity within the universe. It's a story still being pieced together by scientists, each new discovery adding another layer of understanding to this grand, ancient narrative. The processes described here, the nebular hypothesis and the stages of accretion, provide the framework for understanding how our solar system, and countless others throughout the galaxy, came to be. It's a story that connects us to the very origins of our existence, a reminder that we are, quite literally, made of stardust. Mars, the red planet, isn't just a rusty-colored sphere hanging in the night sky. Beneath its thin atmosphere lies a world of surprisingly complex geology, a story etched in ancient rocks and revealed through the tireless work of robotic explorers. For a long time, it seemed a desolate, cold landscape, but increasingly, we're discovering a history of intense activity, a history that suggests Mars might have been far more hospitable than we once thought. The key to unlocking this history lies in understanding the planet's volcanic past, its shifting crust, and the tantalizing clues that might point to the possibility of ancient life. The most striking evidence of this past activity is found in the vast plains of the northern hemisphere, particularly in regions like Tharsis and Elysium. These areas are dominated by enormous shield volcanoes, far larger than anything found on Earth. Olympus Mons, the largest volcano in our solar system, rises nearly 3 times higher than Mount Everest, a behemoth created not by violent eruptions, but by the relentless, slow accumulation of lava over billions of years. It's a truly awe-inspiring sight, even from the distance of a rover. Smaller, but still impressive, shield volcanoes like Ascreus Mons and Pavinus Mons are scattered across the Tharsis region, forming a volcanic province that dramatically altered the Martian landscape. These volcanoes aren't built by explosive, cone-shaped eruptions like those that form stratovolcanoes on Earth. Instead, they're the result of vast, flowing rivers of basaltic lava, a relatively fluid, low-silica magma that spread across the surface, creating gentle slopes and smooth, undulating plains. Scientists believe that the Martian mantle, the layer beneath the crust, is relatively small, contributing to the creation of these massive, shield-like volcanoes. Beyond the giant shield volcanoes, Mars also exhibits evidence of more localized volcanic features. We've found numerous volcanic cones, lava channels, and volcanic flows across the planet, providing a more detailed picture of the volcanic activity that occurred at various times. The Elysium Planitia region, for example, is characterized by a complex system of volcanic flows and fractures, likely associated with the eruption of Elysium Mons, another significant volcano. These smaller eruptions, coupled with the broader shield volcanoes, paint a picture of sustained volcanic activity for a substantial portion of Mars's history. The composition of the lavas themselves provides crucial information. Analysis of Martian meteorites, rocks that fell to Earth from Mars, reveals that the lavas were predominantly basaltic, similar to those found on Earth's Galapagos Islands. This suggests a relatively stable mantle composition over long timescales. However, the story of Mars isn't just about volcanism. There's compelling evidence that the planet's crust has undergone significant changes over time, far beyond simply being shaped by lava flows. Crustal dynamics, the movement and deformation of the planet's outer shell, have played a crucial role in shaping the Martian surface. The presence of extensive grabens, large, fault-bounded depressions, and wrinkle ridges, formations created by tectonic extension, indicates that Mars was once subjected to significant stretching and thinning. These features suggest that the crust was once thicker and more rigid, but has since been dramatically weakened and fractured. The mechanism behind this crustal deformation is still a subject of ongoing research, but scientists believe it's linked to the planet's internal heat, primarily generated by the decay of radioactive elements in the Martian mantle. This heat drives convection currents within the mantle, causing the crust above to move and deform. The Tharsis region, in particular, is thought to be the result of this convective process, with the uplift of the volcanic province driven by the movement of hot mantle material. Evidence of this process is found in the abundant faulting and fracturing observed across the region. But perhaps the most exciting aspect of Martian geology is the search for evidence of past habitability. The history of volcanism and crustal deformation has created a complex interplay of conditions, and there's a growing belief that Mars may have possessed liquid water on its surface for extended periods. The presence of hydrated minerals, such as clays and sulfates, indicates that water interacted with the Martian rocks, further strengthening this hypothesis. These minerals formed as water reacted with the volcanic rocks, a process that could have provided a source of energy and chemical ingredients for microbial life. Furthermore, the discovery of ancient lake beds and river channels, now largely dried up, suggests that Mars once had a warmer, wetter climate. These features offer potential locations where life could have thrived if it ever arose. Rovers like Curiosity and Perseverance are actively exploring these ancient environments, searching for signs of past microbial activity, perhaps in the form of fossilized microbial mats or chemical biosignatures preserved within the rocks. The ongoing investigation of Gale Crater, Curiosity's location, continues to reveal a complex history of fluvial processes and potentially habitable environments, providing tantalizing glimpses into the possibility that Mars wasn't always the cold, barren world we see today. The search continues, fueled by the knowledge that the planet's geological past holds the key to understanding its potential to have once harbored life. Jupiter, the giant of our solar system, is a world of swirling gases and incredible forces. Its sheer size, larger than all the other planets combined, creates a dramatically different environment than anything we experience on Earth. But amidst this vastness, there exists a phenomenon so remarkable, so persistent, that it has captivated scientists and stargazers for centuries: the Great Red Spot. This isn't just a large storm. It's a swirling, crimson wound in Jupiter's atmosphere, a testament to the powerful dynamics at play within this gas giant. For hundreds of years, observers, from Galileo himself, have tracked its movements, trying to understand its origins and its ongoing existence. The Great Red Spot is a giant anticyclonic storm, meaning it rotates in a circular pattern without converging or diverging winds. Unlike hurricanes on Earth, which tend to weaken and dissipate relatively quickly due to friction with the ocean's surface, the red spot has endured for at least 350 years and potentially much longer. Its diameter is currently around 110,000 kilometers, roughly the size of 3 Earths, and it's moving slowly westward at a rate of about 2 to 4 kilometers per hour. This slow pace belies the incredible energy contained within its swirling currents. What drives this colossal storm? The key lies in Jupiter's atmosphere, which is primarily composed of hydrogen and helium, much like the Sun. However, unlike the Sun, Jupiter has a substantial, albeit thin, atmosphere with distinct layers. These layers exist due to the enormous pressure and temperature variations within the planet. The upper atmosphere, where the red spot resides, is characterized by jet streams, fast-flowing currents of gas moving in opposite directions. These jet streams, ranging in speed from 300 to 600 kilometers per hour, are created by the planet's rapid rotation. Now, the red spot isn't simply riding on these jet streams. It's interacting with them, amplifying their effects. The storm's rotation itself generates additional, smaller jet streams that spiral outwards from the center. These newly formed jet streams are then caught and intensified by the red spot's rotation. It's a self-sustaining feedback loop, creating a situation where the storm's energy continues to grow and maintain its immense size. The swirling motions generate strong vertical winds that move both horizontally and vertically, which further contribute to the storm's complexity. Observations made by the Voyager 1 and 2 spacecraft, and more recently by the Juno mission, have revealed fascinating details about the red spot's interior. Juno, equipped with an atmospheric probe, descended through the upper atmosphere, directly sampling the conditions within the storm. The probe discovered that the red spot's depths are significantly colder than the surrounding atmosphere, reaching temperatures as low as -145 degrees Celsius. This temperature difference is a critical factor in the storm's longevity. Furthermore, the probe revealed that the red spot is surrounded by a ring of less dense, lighter gas. This ring, believed to be formed by the uplift of material from lower in the atmosphere, is thought to be a consequence of the storm's powerful rotation and vertical wind shear. The ring provides a source of material that feeds back into the storm, helping to maintain its size and intensity. Scientists believe that the ring is dynamic, constantly shifting and changing shape in response to the storm's movements. Interestingly, the red spot isn't always the same color. While it's most frequently observed as a deep crimson, it can shift through shades of orange, brown, and even pink. This color change is attributed to complex chemical reactions occurring within the storm's clouds. The precise composition of these clouds and the factors driving the color variations are still areas of ongoing research. Scientists believe that the color changes are influenced by the abundance of ammonia and acetylene, which are abundant in Jupiter's atmosphere and play a crucial role in the photochemical processes that produce the distinctive hues. Recently, the Great Red Spot has been shrinking. Observations made over the past century show that it has diminished in size, although its intensity remains high. This shrinkage is a cause of considerable scientific interest. Some researchers theorize that it's being consumed by smaller, turbulent storms that are emerging around its edges, effectively eating away at its boundaries. These smaller storms, fueled by the energy of the red spot, are disrupting the storm's structure and causing it to gradually dissipate. Other models propose that changes in Jupiter's jet stream configuration may also be contributing to the red spot's decline. The future of the Great Red Spot remains uncertain. While its long-term survival is not guaranteed, it is a stunning reminder of the powerful forces at play in our solar system. It's a testament to the chaotic beauty of planetary atmospheres and the ongoing scientific quest to understand these complex systems. The red spot continues to fascinate and challenge scientists, and hopefully, future missions will provide even more insights into this enduring giant of Jupiter's atmosphere. Saturn, the jewel of our solar system, is known for many things: its beautiful rings, its prominent position in the sky, and its surprisingly dense atmosphere. But perhaps the most captivating feature of this giant planet is, without a doubt, its ring system. It's not a solid shell, like a planet's crust, but a staggeringly complex and dynamic collection of particles, each one a tiny fragment of a story waiting to be understood. These rings aren't just pretty. They represent a fascinating puzzle piece in our understanding of planetary formation and the processes that shape our solar system. The rings themselves are comprised of billions upon billions of icy particles. These particles, ranging in size from minuscule grains, less than a millimeter across, to chunks as large as houses, are predominantly composed of water ice, mixed with traces of other materials like carbon dioxide, methane, and ammonia. The ice isn't pristine. It's heavily contaminated with dust and rock, reflecting sunlight in a dazzling array of colors. This isn't a uniform gray band. Close observation reveals streaks of blue, white, and gold, created by the varying compositions and sizes of the particles. The larger particles scatter blue light, while the smaller ones reflect yellow and gold hues. Scientists believe that the rings are relatively young, perhaps only a few 100 million years old. This is a remarkably short time in the history of the solar system, which is 4.5 billion years old. The prevailing theory for their origin centers around the disruption of a moon, or perhaps multiple moons, that once orbited Saturn. This moon, initially named Mimas, was a substantial body, roughly the size of Earth's moon. It resided within Saturn's orbit, existing as a mini-planet. However, Mimas wasn't stable. Gravitational interactions with Saturn and perhaps other nearby celestial bodies, like Neptune, began to pull it apart. This process, called a Roche breakup, is a well-known phenomenon. When a celestial body gets too close to a massive planet, the planet's gravity overwhelms the body's own self-gravity, causing it to disintegrate into a ring of fragments. The tidal forces, the difference in gravitational pull on opposite sides of the moon, literally tore it apart. Now, these rings wouldn't remain intact forever. Without anything to hold them together, the particles would simply drift away into space. This is where the enormous shepherd moons come into play. These moons, named Pandora and Pan, are approximately 200 kilometers in diameter and possess an incredibly eccentric and inclined orbits. They don't orbit Saturn in a neat circular path. Instead, they trace out complex, tilted trajectories. Pandora and Pan are essentially gravitational guardians. Their precise orbits prevent the ring particles from spreading outward and collapsing. They maintain a constant, subtle gravitational influence, acting like cosmic corks, keeping the ring system contained. They shepherd the particles, subtly curving their paths and preventing them from escaping into the outer reaches of the system. The orbits of Pandora and Pan are not static. They are constantly changing due to gravitational interactions with the rings themselves and with Saturn. These interactions cause them to spiral inward and outward, creating a dynamic dance that shapes the structure of the rings. Furthermore, the moons themselves are subject to continual bombardment by ring particles, which constantly erode their surfaces. The ring particles act like tiny, persistent sandblasters, slowly grinding down the moon's surfaces. The rings aren't a single, solid sheet. Instead, they're composed of thousands of ringlets, each a narrow band of particles orbiting Saturn at slightly different angles. These ringlets are evidence of the chaotic processes occurring within the system. They're sculpted by the gravitational forces of Saturn, the shepherd moons, and the interactions with the ring particles themselves. Scientists are continually studying the rings to learn more about their composition, their dynamics, and their history. They use telescopes, both ground-based and space-based, to observe the rings in detail, tracking the movement of the ring particles and studying the structure of the ringlets. Recent missions, like the Cassini spacecraft, have provided unprecedented data, revealing a level of complexity and dynamism that scientists hadn't fully appreciated before. Cassini's close-up observations have revealed gaps and divisions within the rings, providing further evidence of the gravitational influence of the shepherd moons and the ongoing processes shaping this incredible system. The rings of Saturn represent a continuous cycle of creation and destruction, a testament to the powerful forces at play in the solar system. They're a beautiful and complex reminder that even the most seemingly stable systems are subject to constant change, and that the universe is full of surprising and wondrous phenomena. It is truly a spectacular system, and one that continues to challenge and inspire our scientific curiosity. The solar system isn't just planets orbiting the sun. It's a surprisingly complex dance of gravity and debris. Far beyond the familiar orbits of Mars and Jupiter lies a vast region known as the asteroid belt. It's a sprinkling of rocky remnants, the leftover material from the solar system's formation, and understanding its movements and makeup is a crucial piece of the puzzle in how we view our cosmic neighborhood. For a long time, it was thought of as a chaotic jumble. a dangerous zone that spacecraft would inevitably crash into. However, modern observations have revealed a far more intricate and stable system. The key to understanding the asteroid belt stability lies in something called orbital resonance. Planets, including Earth, exert gravitational forces on each other. These forces aren't perfectly aligned, so the orbits are slightly tilted and elliptical. But some asteroids, particularly those in the main belt between Mars and Jupiter, are caught in a delicate balancing act with Jupiter itself. These asteroids' orbits are influenced by Jupiter's gravity in a way that keeps them from colliding with each other. Specifically, many asteroids follow inclinations, angles of tilt, that are multiples of 35 degrees, a number directly linked to Jupiter's orbital position. This creates a sort of gravitational tuning fork, where the asteroids' movements reinforce each other, maintaining a relatively stable configuration. It's not just Jupiter. Other planets like Saturn and Neptune also play a role, though their influence is generally less pronounced. The system is a network of gravitational interactions, a cosmic ballet where each body subtly affects the other's paths. This isn't a simple, uniform zone of chaos, but a dynamically complex region where the overall structure remains remarkably consistent over millions of years. Scientists use sophisticated computer models to simulate these interactions, constantly refining our understanding of the belt's behavior. But the asteroid belt isn't just a collection of rocks. It's astonishingly diverse in terms of composition. Scientists have identified 3 primary types of asteroids, each with a distinct story to tell about the solar system's infancy. C-type asteroids, which make up roughly 75% of the belt's population, are characterized by their dark, carbon-rich composition. They're often dull gray or black and reflect very little sunlight. These are believed to be the remnants of the primordial material from which the planets formed, largely untouched by the intense heat of the early solar system. Then there are the S-type asteroids, which are silicate-rich and similar in composition to Earth's mantle. They tend to be lighter and have brighter surfaces than C-types. D-type asteroids, the rarest of the 3, are composed primarily of carbon-rich materials and are often reddish in color. They're thought to represent material that was closer to the Sun during the solar system's formation and experienced higher temperatures. Beyond the main belt, smaller populations of asteroids exist. The Trojans, for example, share Jupiter's orbit, residing in stable locations ahead of and behind the planet. These Trojans are particularly interesting because they provide a snapshot of the conditions present during the solar system's early stages. Furthermore, there's a significant population of near-Earth asteroids, NEOs, which is where things become a subject of significant concern. NEOs are asteroids whose orbits bring them relatively close to Earth. They range in size from tiny pebbles to objects several kilometers across. While the vast majority pose no threat, a small fraction represents a potential hazard. The size and composition of these asteroids, coupled with their orbital paths, determine their risk level. Larger asteroids, even those tens of meters in diameter, could cause significant regional damage if they were to impact Earth. Scientists are actively monitoring NEOs using telescopes around the world. The Near-Earth Object Surveillance System, NEOSS, is a global effort that tracks these objects and calculates their trajectories. This information is crucial for assessing the risk of an impact and developing potential mitigation strategies. Currently, the most discussed threat comes from asteroid 1999 JD, a roughly 100-meter object that passes close to Earth every few years. While its passage poses no immediate danger, it highlights the importance of continued observation and research. The potential consequences of a large asteroid impact are dramatic. A substantial collision could trigger massive earthquakes, tsunamis, and widespread wildfires, disrupting global climate and causing immense devastation. However, it's important to remember that the chances of a catastrophic impact by a significant NEO are relatively low, and our ability to detect and potentially deflect these objects is constantly improving. Advanced techniques, such as kinetic impactors, essentially slamming a spacecraft into an asteroid to alter its trajectory, and gravity tractors, using a spacecraft's own gravity to gently pull an asteroid off course, are being explored as potential methods of planetary defense. Ultimately, the asteroid belt is far more than just a leftover ring of rocks. It's a window into the formation of our solar system, a dynamic region of gravitational interactions, and a reminder of the potential hazards lurking in our cosmic neighborhood. Continued research and monitoring are essential for understanding and managing these risks, ensuring the continued safety and well-being of our planet. If you're still awake and enjoyed this exploration, please consider liking this video and subscribing to Ultimate Sleep Doctor. Together, we can soothe more wandering minds, one peaceful night at a time. Our journey through the solar system has now quietly concluded, its distant planets gently receding into the darkness. Let your thoughts drift, calm and unhurried, carried on the starlight until sleep finds you. Good night.